This represents 2 of the 4 dimensions. Just as the Earth appears flat to us when we are looking at only a tiny portion of it, this curved space-time will also appear flat if we zoom in and look at only a tiny section. If we approximate this region with the mathematics of flat space-time, we can define an axis for one of the 3 spatial dimensions and an axis for time. Different observers in this region moving relative to each other will have different orientations for these axes in accordance to the rules of special relativity. Suppose we move forward along the time axis seen by the observer moving in the direction of the red arrow. Our approximation for flat space-time is now no longer valid. We correct for this by rotating our red arrow along the line 90 degrees to the surface. We can now create a new flat space-time approximation for this new region. We can use this new approximation to again move forward in the direction of the red arrow. If we repeat this over and over again, using exceedingly small time steps, we get the path that the object will follow through curved space-time. The path appears curved to us, thereby creating the illusion of a gravitational force. To describe 4-dimensional space-time, we need 4 coordinates, which we will refer to as x0, x1, x2, and x3. The numbers 0 through 3 are index values, not exponents. Einstein's field equations remain valid no matter what coordinate system we choose. None of the coordinates necessarily need to correspond to the time coordinate of any observer. Curved coordinates can also be used to describe flat space-time. In order to better understand the critical concepts, let us first focus on a flat 2-dimensional space. The following arrows show the direction in which our position will change if we increment one of the coordinates at various points in space by a small amount. These arrows are what we refer to as the basis vectors. Let's move one of the basis vectors by exactly 1 unit as shown. The rate at which the basis vector changes is described by the white vector. The white vector can be represented as a linear combination of the 2 basis vectors at this point. Let's replace the numbers with the following symbols, each of which has 3 index values. The index value at the top indicates which basis vector is multiplying. The two index values at the bottom indicate which basis vector is moving and in what direction. These symbols indicate the rate at which the basis vectors are changing at each point in space. The basis vectors could be changing because we are using a curved coordinate system in a flat space-time. Or the basis vectors could be changing because we have a curved space-time, even though we have coordinates as straight as possible. Suppose we have a curved four-dimensional space-time with coordinates as straight as possible, where x0 represents time, and x1 through x3 represent the three spatial dimensions. In situations where Newtonian physics gives accurate approximations, the acceleration due to gravity is approximately equal to the following symbols related to the curvature of space-time. In these cases, the gravitational acceleration is approximately equal to the rate at which the basis vector for time changes as it moves forward in time. This change is due to curvature. In order to know how a vector changes due to curvature, we need to know how to move it from one point to another. Suppose we move a vector by an exceedingly small amount without changing the direction it is pointing. Every time we do this, we need to take the curvature into account by rotating the vector along the line 90 degrees to the surface. If we repeat this over and over again, we can move a vector over long distances, which we refer to as parallel transport. If we parallel transport a vector in flat space-time, when we return the vector to its starting position, it will always still be pointing in the same direction as before. The same is not necessarily true in curved space-time. We can define the curvature of space-time in terms of how much the angle of a vector changes when it returns to its original position. But this angle also depends on the size of the area that the vector travels around. When the vector travels around this area, it is rotated by 90 degrees. If we double the area, double the amount by which the vector is rotated. We can therefore define the curvature in terms of the amount by which the vector is rotated divided by the size of the area around which the vector traveled. Note that when the vector traveled around the area in the counterclockwise direction, The vector rotated counterclockwise.